Long-horizon LLM agents are getting better at chaining tool calls, retrievals, and memory writes. But they have a quiet failure mode that standard evaluation completely misses. They don't crash. They don't hallucinate wildly. Instead, they settle on one interpretation of the evidence early on, and then spend the rest of their run defending it. We call this premature commitment. And it's why a single final answer, or even cross-run output agreement, can't tell you if an agent is actually reasoning well or just confidently wrong. So how do we catch it? The researchers behind this work asked a deceptively simple question. Does that internal settling leave a measurable signature in the model's hidden states? They defined representational commitment as cross-run hidden state convergence at a fixed reasoning step. In practice, that means running the exact same prompt multiple times at a moderate temperature, extracting the hidden state at the last token position of a specific step, and measuring the mean pairwise cosine similarity across those runs. Cosine similarity here measures the angular alignment in high-dimensional activation space. High similarity across runs that saw different intermediate observations means the model has locked onto a stable interpretation. Low similarity means the representation is still fluid, still depending on the particular evidence path. They tested this on Llama 3170, running a RayAct agent on HotpotQA, executing 10 runs per question at a temperature of 0.5. They tracked the hidden states across layers 0 through 80, and compared activation similarity against behavioral consistency. For behavior, they didn't just look at output agreement. They used the coefficient of variation of step counts, which is scale invariant and captures trajectory length variance regardless of mean chain length, plus action sequence diversity, which measures how tightly the actual tool call paths cluster. The result was striking. At step 4, hidden state similarity became strongly negatively correlated with behavioral variance. Questions whose representations converged across runs behaved dramatically more consistently. The effect wasn't a fluke. It survived a 10,000 iteration permutation test, held up under Bonferroni correction over a 66-cell step-a-layer grid, and peaked sharply at layer 40. And this wasn't a single model artifact. They replicated it across QN2, 5-72B and Phi314B. The correlation sign stayed the same, but the peak layer shifted. Llama peaked at 50% depth, QN at 80%, and Phi3 at 40%. On StrategyQA, where reasoning chains are shorter, the signal actually peaked a step earlier at step 3, with a correlation coefficient dropping to negative 0.83. This tells us commitment is a robust, architecture-agnostic phenomenon, but its exact temporal and spatial signature adapts to the task and model size. Now here's the part that final score evaluation completely hides. This diagnostic tracks process consistency, not correctness. The researchers explicitly tested committed correct versus committed wrong questions. In activation space, they are statistically indistinguishable. A non-significant difference here means the model's internal convergence signature is completely orthogonal to whether it's right. It behaves like a well-calibrated classifier that can be confidently wrong. This is critical. If you only look at agreement, a confidently wrong agent looks as reliable as a correct one. Representational commitment tells you whether the agent has settled. It does not tell you if it's settled on the truth. So what do we do with this? First, runtime detection. By feeding step 4 hidden state profiles into a logistic classifier, they built a monitor that flags inconsistent trajectories with an AUROC up to 0.97. AUROC here measures the monitor's ability to separate consistent from inconsistent runs. It degrades gracefully, hitting 0.81 with just 3 runs, which means you can early exit committed trajectories to save compute. Second, intervention. They tested a prompting strategy that explicitly asks the agent to commit to a reasoning strategy before continuing. Compared to a token-matched semantic filler, the commitment prompt cut behavioral variance by 28%. But again, accuracy remains statistically unchanged. The intervention amplifies whatever trajectory the model is already on. It tightens the process, but it doesn't fix the underlying reasoning. A bootstrap mediation analysis confirmed the representational shift accounts for the variance reduction, though it showed inconsistent suppression rather than clean full mediation. The natural next step is using this signal to route self-consistency compute. You'd think you could spend more samples on uncommitted questions and fewer on committed ones. And it does help, but only modestly. On harder benchmarks, the hidden state signal beats fixed sample self-consistency by a couple of points, but it's quickly matched by simpler output-based adaptive consistency, which just stops once answers agree. The researchers are upfront about this. It's an honest negative for compute routing, and they leave a deployable hidden state router to future work. They also note the limitations. The disentanglement from observation overlap is partial, single-layer activation steering gave mixed results, and the mediation analysis showed inconsistent suppression. They also point out that a proper equivalence test, like TOSD, is needed to formally claim correctness agnosticity, and that chain of thought can sometimes be unfaithful to the true reasoning path. Premature commitment is a fundamental bottleneck in multi-step agent reasoning. It's invisible to standard metrics, but perfectly visible in the geometry of hidden states. This work gives us a compact, highly predictive diagnostic for a hidden process failure, with clear boundaries. It's excellent for measurement, variance reduction, and early exit strategies. but it's not a silver bullet for accuracy, and it's not yet a better compute router than output-level methods. As agents take on longer, more consequential tasks, understanding when they've locked in, and when they're still open to new evidence, will be the difference between reliable automation and quiet, consistent failure. If you're working on agent reliability, representation engineering, or test time compute allocation, this is a must-read. Let me know in the comments how you're currently handling trajectory variance in your own pipelines. And if you want to dive into the math, the full permutation tests, or the supplementary ablations, I'll link the preprint and code in the description. Thanks for watching.